this is very important to know, to manage, dahil lahat ng bagay, lahat ng physical na bagay may ganito. Okay. Kung last time, just to recap, isa sa mga properties ng mga instruments or mga systems output nila. And this can be expressed, one way of expressing among many things. One way of expressing it is through input-output curve. This is steady state. All cell system take time. Yeah. Okay. All systems take time to react. So for example, this is a sensor, and you shone light on it. So kunyari, flashlight was off and then it suddenly turned on. So in time, this is a plot of the flashlight intensity in time, ano? And at a certain time, say usually ang start time natin t equals 0, flashlight is turned on. System will in general not react. At time t equals 0, okay, it will probably build up. Whatever is the mechanism for sensing the light, it will take time to build up. And ito yon. You see that there are two parts in the reaction or the system. So here, the output of the system response. This is one among the many possible system responses to a step function. A step function is a representation of turn on condition. Turn on condition. Okay, something is from off state, switch to on. Let's call G for traditional reasons. Okay, so this is the input. It could be any form of energy, and G could be a sensor, for example. Sensor. Okay, and here in 1/8, what we have is sensors in any energy, whether it's light, it's heat, or mechanical or energy, and together doing electrical response, or eventually it's converted, say, into voltage. So from energy to electrical energy, yun yung habol natin dito sa ano na to, sa course na to. It takes time to respond. Let's look at it at more detail, this response to a step function. Okay. Now, notice that one of the possible ways an output of the system would look like. So for example, this is the input, no? This is the level of the final input, right? Okay, t equals 0. This is in time. And this is the of the sensor. Yan. Okay. Now, here's the two things that you need to remember. There's a period where the system takes time to you. Okay, the transient state. This is for us. Output more. This is called the steady state.
Hi, Ma. Ma'am, excuse me. Medyo choppy po ata kayo.
Yeah.
Ma'am, medyo choppy po ata.
I am?
Yes.
you. Sige, I will transfer to where the signal is stronger. Sige, wait lang. I'm sorry. Thank you for feedbacking that.
Thank you rin po, ma'am.
Lipat lang ako mas malapit sa antenna. Sorry. Thank you for telling me. As I was saying, ito, I hope I'm no longer choppy. How are you? Diretso na? Choppy pa rin? Hello, hello?
Malinaw na po.
Hi, ma'am. I think it's better na po.
Salamat. Okay. So as I was saying, if you test an instrument or a sensor with a step input, and it's usually done by just simply turning it on or in introducing a signal which is turned on, and the level of the signal is constant after turn on condition. No? You will notice that the system or the sensor will behave as shown in the red line. There will be a period called the transient state where it is just trying to reach from zero, no, it's just trying to reach the final value. And after it has reached a final value, that is what is known as the steady state, because if the input doesn't change anymore, it will just stabilize to that value, okay? Now, as I said, input-output curves, which are used for calibrating instruments, is measured during the steady state. You don't measure an input-output curve here kasi hindi yan yung final value, right? Mali yan kapag iyan ang ginamit mo for input-output curve. You measure kapag steady state na yung system. Now, it has bearing in our first experiment. In our first experiment, you will practice getting the input-output curve of a rotation sensor. Okay. Also, in another sensor, the light sensor, for example, an LDR, you will also observe this kind of behavior, right? So imagine you shine an LED. So an LED has a quick response, a very fast response. Sorry, let's draw an LED here. Yellow, green. So we have an LED here. It's yellow, green. Okay. And then you'll program this to blink on and off, which means if you look at it in the plot, yung input signal niya, technically, you can drive this with a square wave and it would look more or less like this, on and off condition, no? Now, how a sensor such as a light-dependent resistor read this? Okay? And what you will observe is, posibleng ganito yung reading niya. Depende dun sa kung gaano kabilis yung, yung sensor. It could happen that there is a time na ganyan, tapos pag mag-off na, gaganyan siya. Okay? Ganyan na. And this part here na pagpababa, may transient response pa rin is because meron pang mga residual energy na natira doon sa sensor and it's petering out. Ganyan. You also observe this behavior in, for example, charging or discharging capacitors. But the key here is if you are getting an input-output curve, always do so. Always make sure that you are measuring it during the steady state. Now, going to the transient state, back to the transient state. So the steady state is medyo boring because if your input is constant, it will also be constant. But however, there is another thing to watch out. It can happen also that the steady state would look like this. No? After reaching, it's like this. Doesn't quite get to the final output. It can happen sometimes. And in this case, this level here is called the steady state error. This is also needed to be noted. Why? Because this will reflect in the input-output curve as some bias. There. Now, let's go back to the transient state. There are many ways of finding out up to when is the transient state done. For this kind of curve, this is known as, every time you see this kind of behavior na para siyang charging capacitor, this is the signature of what is known as a first order system. Okay, a first order system has a characteristic exponential approach to the final value. Now, for example, if the system is output is y of t, okay, and the input is a unit step. For a first order system, the output is expressed as this way, and we will derive it in a bit. No? This is the analytic version of the plot that you see earlier. Itong parang exponentially nagde-decay yung difference between the final output and the input, the unit input. Okay. Now, for first order system, so this letter A is a parameter of importance. This is called the inverse of the time constant. Okay. So tau is what is known as a time constant. Okay. When A equals 1, that means y of t is equal to 1 minus e to the minus t. Oh, sorry. Oh, tama. Okay, tama yan. And if you plot this, sorry, mali. sorry. May mali akong sinasabi. Ulit. When t is equal to tau, sorry. Nalingat ako doon. Then, the output, when the time is equal to the time constant, then this becomes 1 minus e to the minus 1, which is a number. It's actually 0.63 approximately. Okay, if you calculate this, 1 minus e to the minus 1 is approximately 0.63. Okay, so what does that mean? You know this before, I believe you've seen this before, but the importance here in sensors or in measurement is that when the signal, so for example, is the final output, let's normalize the final output as 1. When the signal from the output of the sensor reaches 1 minus e to the minus 1, anong ibig sabihin nun? The time is equal to the time constant. So suppose this is the 0.63 mark. At that value where the output is 0.63, the time it is at that is equal to the time constant. So essentially the time constant tau is when the output is 63% of the final output or steady state output. Okay. And it is engineering practice, no, to measure or to assume that the steady state is at 5 times the time constant. Okay? Meaning, this is t equals tau. So bilang ka ng 5 times, yan, sure na sure ka na at this time, yung measurement mo dito ng value is at steady state. So that's just an engineering practice. Sometimes, some people use 3 times tau. So minsan, kahit dito, na-assume na nila na steady state yan. Well, to be safe, you can go up to 5 tau. Why is this necessary? Again, bakit ito ulit necessary? I must emphasize, when you do an input-output calibration curve, you have to measure the output at steady state. Never measure it maaga pa, because you are not measuring the full value or the full output of the system. Okay? This is the reason why. Kapag naalala nyo yon ng bata kayo, di ba? Pero ngayon kasi, ano na eh, handheld na thermometer eh. Sino yung mga nakaabot na nung bata pa sila eh, ang pang-measure ng temperature ay thermometer na linalagay sa kilikili. Naalala niyo yan? Ewan ko kung naabutan niyo yan. But remember anong ginagawa ng nurse? You have to wait mga 2 minutes, di ba? Because it takes time for the liquid in the mercury, or rather in the liquid thermometer, to reach the final temperature. Okay? So the liquid in the thermometer expands, but it takes time to stabilize to the final output. Okay? So it takes, and usually it's around 2 minutes. And then they read. Imagine nyo, pag read pa lang 1 minute. Di ba? Parang hindi pa tapos kang basa, hindi pa tapos mag-transfer yung energies from the heat energy from your body to the liquid. So hindi pa iyon yung actual temperature mo. This is the reason. Okay? So please remember why the transient, when the transition between transient and steady state happens, by rule of thumb, it is 5 times the time constant. How do you know kung ano yung time constant? If you have this graph, if you have a graph of the sensor and it's given to you this way, okay, you can know the time constant. You will know the time constant. And then you can say, okay, I have to wait 5 times time constant before I capture the data at this point. You can also measure this yourself, okay? Again, by introducing an input, which is a step function, okay? So you will measure it yourself. You can also measure it yourself. Also, one other way is by looking at first principles. A first order system can be described as this. In terms of the Laplace transform, a first order system has a description or a function given by this. Again, A is related to the time constant. And what is S? S here is a variable, a complex variable, which has a real and imaginary part. So S is a variable which has units of frequency. It's actually a complex frequency variable. Okay. The omega part, or sorry, the sigma part is known as the exponential frequency. It has units of 1 over time. And the omega part is the radial frequency. Okay. There. So every time you see a system which is described in terms of the Laplace transform as having this form, then you say it is a first order system. Okay. Can we do that given components of the system? Yes, we can. Now we go back to the lecture that I gave earlier. Stop sharing muna and I'll show you that lecture note. I'll switch back to my... May question ba tungkol dito? Wala naman? Okay.
Wala po.
This is the... Okay, so this is the first order system. Before I go back to my laptop, let me continue on to a second order system. At least yung mga characteristics lang muna before we derive. Okay, so this is the first order system. The characteristic is simple. It's like this. Okay, we are assuming, and also, by the way, caveat, we are assuming that we are looking at a linear portion of the range of the sensor. Okay, hindi natin ina-assume na nasa non-linear portion tayo. Sa linear part lang tayo. Just to complete the picture, let me talk about the appearance of a second order system response. Okay. Analytically, a second order system would have this form of the Laplace transform or equation or transfer function. So it is second order because the polynomial in terms of the complex variable is second order. There would be damping coefficient, and again the natural frequency omega is frequency, but it is subscript by n because it's known as the natural frequency. There is s here, and then omega n squared. So you see that, sorry, shift. Okay, so you see that the form of the second order system, okay, is quadratic, the denominator. And there are two parameters of note: the natural frequency and the damping coefficient. How do you know if a system is second order? If you once again hit the system with a step function and the behavior is any one of the four, it is a second order system. A second order system has a richer dynamic. Okay? So sabihin natin ito yung step function. At time t equals 0, it turns on. Okay? And let's normalize the final value. So it's a unit step. Ganyan. All right. An underdamped second order system will have this characteristic. The moment you turn on the system or you excite it with a unit step, it can, so like the first order system, it will try to rise and meet the final value, but it can overshoot. Straight line yan. Like this, nag-overshoot siya, and then it will return back. Medyo mag-overshoot din siya pababa, and then rise up again because the excitation is just steady, and then eventually settle to the final value. Okay. Once you see this overshoot, okay, sure ka agad na this is a second order system. No first order system does this. Okay? The ringing that you see here has something to do with the natural frequency of the system. No? All objects actually has a natural frequency of vibration. For example, a rod that is tied at one end, like an antenna on a car, has a natural frequency of vibration such that if the motor revs at that frequency, makikita nyo mag-oscillate yung antenna by itself, right? So there are many objects, in principle, all objects can vibrate, and all objects have a natural frequency. And this is manifested in this vibration here because this is that showing up. Okay? The damping coefficient affects the peak here. Okay? The damping coefficient can range from a number. If the damping coefficient is a number from 0 to 1, it's not 0, it's not equal to 1, it's not greater than 1, it's between 0 and 1, then we will see this underdamped condition. So long as, again, the damping coefficient is between 0 and 1, we will observe this underdamped and overshoot condition. All right. When it comes to steady state response, okay, ito naman ang kailangan tignan. Experimentally, you take a look at when it reaches 0.1 and when it steadies up to 0.9. Okay? Also, titignan mo rin kung lumagpas na siya ng 1.1. Okay. For a second order response, kapag hindi na siya lumalagpas between 0.9 and 0.1, yun na yung start ng kanyang, in a way, time constant. After that, nagsisteady na siya. So, it can happen kasi that this oscillation can go on and on and on, pero it's just oscillating in the about the final value. Which is why kapag na-observe mo na hindi na siya lumalagpas between 1.1 and 0.9, pwede mo nang sabihin na okay, it's now at steady state. Okay? So for example, kunyari dito hindi na siya lalagpas ng, or rather here, hindi na siya, after this hindi na siya lalagpas ng 1.1 or 0.9, then you can say that this is already at steady state. Then you can start measuring from here. Okay. Yeah. Any other higher order system is just a combination of a second order and a first order. Okay? So hindi na natin pag-usapan yung third order, fourth order kasi they can be decomposed into a combination of first order and second order and even zeroth order. Okay? Now, as I said, we are dealing with electronic systems, no? So ang gusto nating malaman is, given the components, can we know kung anong magiging, and their combination, anong magiging behavior niya in time? Okay? Ano yung magiging response niya, transient and steady state? Okay? So, transient, steady state, overshoot is in the transient response, and then steady state is kapag medyo nasa loob na yung final output. Okay. Now let's go back to the idea of some linear components. For this, I need to transfer to my laptop. Kaya please give me a few moments para mag-stop share and then I'll go to my other machine. Okay? Meanwhile, may mga tanong ba?
Wala po so far.
Stop share. Stop share.
Ma'am, ako po meron.
Yes, please.
Yung second order, same lang ba siya ng y of t with the first order?
No.
Okay.
Ibang-iba. The medyo mas complicated and there are 4 possible behaviors. Ang pinakita ko lang is 1, which is underdamped. Okay? So for a second order response, there are actually 4 possible behaviors. Okay? Ang interesting kasi is underdamped because we can extract the system parameters if we observe the underdamped oscillation. Good question though. Okay? Saglit. Lipat lang ako doon sa isang machine.
Thank you, ma'am.
Other questions? If you go back to your Google Classroom and yung notes doon on the linear passive electronic components, and you go to that page, we start here. Now let's talk about the passive linear components and their physics. No, may echo ba? Okay lang. Okay pa? Wala namang echo.
Wala po.
Sige. So, capacitors. So capacitors in general are two parallel plates, conducting plates. There could be a dielectric between them, and each plate, end of the plate is attached to battery and opposite ends of the battery, and therefore the battery provides an electric field in between the plates. Okay, and this is generally used for storing charges, as you know. And in general, charge is proportional to capacitance times voltage. And so I'm just transferring again to the stable connection. Hello? Hi. Hey, there. Here you see that the amount of charge between the plates is proportional to the voltage, and the proportionality constant is the capacitance. And if the voltage across the capacitor changes in time, so will the charge. No? But still the proportionality constant or the capacitance remains the same. And therefore, in terms of the voltage across the capacitor, it can be expressed as Q over T, or charge over C. Okay. Capacitors are also known as condensers. In the olden days, they're also known as condensers. And if you've heard about condenser microphones, it's because there's a capacitor inside that kind of microphone. So there's a plate, parallel plates inside that microphone, and there's a permanent charge actually. But ang nangyayari is, if somebody speaks, the distance between the plates, kasi di ba when there is sound, it's a pressure vibration, a pressure variation, and that pressure causes the space between the plates to change. And because the space between the plates change, ang mangyayari noon ay the capacitance, or C, changes. The capacitance actually is dependent on the property of the plates. It's proportional to the area of the plate, inversely proportional to the distance between them, and the proportionality constant is the electric permittivity. So that's how a condenser microphone works. Dahil nababago niya yung distance between the plates, A is fixed, but the distance between the plates changes because this is a diaphragm which is vibrating as sound is impinging, or rather pressure waves from sound waves are impinging on the microphone. Then this D will change. And so if C will change, the charge is permanent. There's a permanent charge value across the inside the plates, no? But C changes, therefore voltage will change. And this voltage is transmitted, amplified, and brought to a speaker. That's how a microphone works. So please remember this. Capacitance is a geometric property of the capacitor. And now let's go to, and one of the other uses of a capacitor is to remove DC. Okay, because essentially this is an open circuit. If you think about capacitor, it's just empty air, or a dielectric, or anong tawag dito, a semiconductor, not semiconductor, insulator. Exactly, there's an insulator in between that. So if you just put DC inside a circuit, capacitor, walang current na dadaloy dyan. Okay? But pag ang in-enter mo na excitation ay alternating current, ano ba yung alternating current? Pag ganon-ganon lang yung voltage, no? It's just going back and forth, going back and forth. This causes a sort of change in, kumbaga nag-change din yung field between the two plates. And if the frequency is high enough, it's as if this is closed circuit. So therefore, it's a frequency dependent resistor if you think about a capacitor. The higher the frequency, it seems as if the gap is getting closed in a capacitor. So it's used for filtering DC. Can be used to remove a bias if you put it in a circuit as shown here, a DC bias. Let's move on to another passive linear electronic component, electric component, which is an inductor. Okay, if you recall Lenz's law, a current produces a magnetic field, right? And then inversely, if there is a magnetic field, no, there can be a current. Okay. Now, the thing is, because of induction, kapag may napoproduce na current, the parang inertia yan, the system will try to oppose the creation of this current, which is why nagkakaroon ng voltage drop across an inductor when current passes through it. Okay? So we say that a voltage across an inductor is proportional to a changing current. No? So basta may kuryente dyan, may measure tayong voltage across an inductor. An inductor is nothing but a coiled loop, coiled wire, and current is passing through it. It causes an electromagnet, causing the electromagnet is actually causing the induction actually causes an opposing voltage. Okay. And the proportionality constant is what is called the inductance. So long as current is changing in this wire, kung pabago-bago in time yung current na dumadaan dito sa wire na to, you can expect a voltage across this wire. Okay? The inductance, which is the proportionality constant between the changing current and the voltage it produces, is again a geometric property of and the material property of the inductor. It's proportional to the cross-sectional area of the looped wire, which is also known as a solenoid. It's proportional to the square of the number of turns. It's inversely proportional to the length of the solenoid or the coiled loop of wire. And it's proportional, there's a proportionality constant called the permeability. Okay. And this is a property of the inductor itself. All the rest are geometric properties. Okay. So essentially, please remember, changing magnetic flux causes a potential difference. Okay. A current passing through is essentially a number of charge passing through a certain area. So we can express actually current as the rate of charges passing through in time. Okay, and so if you take the derivative of I with respect to t, then in terms of q, it's just the double derivative of q with respect to time. Okay, all right, and here is just a drawing of how an current meter works. You have to put it inside, cut the wire, and then insert the ammeter inside. Okay. Now, to summarize, here we have a list of 3 linear passive components. Passive again means no power supply. The 3 common linear passive components are a resistor. When you measure the voltage across the resistor, it's I times R. I is the current, and R is the resistance resistor, and VR is the voltage across it. In terms of Q, you can express this as dQ over dt times R. Remember, I is equal to dQ over dt. Capacitor, remember, charge is proportional to capacitance times the voltage across the capacitor. Okay, or Q over C is equal to VC. Or since Q dQ over dt is equal to I, you can express it also in terms of I. Or VC is equal to the integral of I over C in dt. Okay? All right? And finally, the inductor. We say that the voltage across the inductor is proportional to the change in current times the inductance, L. And all, in terms of charge, we can have BL, ay kulang ng L. Please put an L here. BL is equal to D squared Q dt squared times L, the inductance. Okay. Okay. Now, I'm assuming that you are familiar with the Laplace transform. I'm assuming that you're done with, no? But one property of the Laplace transform is every time you see a function f of t and you want to take the Laplace transform of that, the way to do it is multiply the function by this kernel e to the minus st. Remember s, that's our complex frequency, and integrate in our case, we integrate not from negative infinity to infinity, but from 0 to infinity. Alam niyo kung bakit? Because all our input signals will be 0 before t equals 0. And everything will start after t equals 0. That's why we integrate not from negative infinity, but we integrate from 0 to infinity. Okay, so performing this operation leads you to the Laplace transform of the function f of t. It becomes f of s. It becomes a function of the complex variable s. All right? Now, once again, please remember, s is a complex frequency. And S has units of 1 over time. Okay, S has exponential and vibrational or radial frequency components, the real part and imaginary part. Okay. Okay. Remember also that what we mean, we use the imaginary number I, diba? But in our case kasi, I has a special meaning. It's the current. So when you talk about electronics, don't use I. We will use J, no, to denote square root of -1 from now on. Okay. Now, in general, kaya siya tinatawag na complex frequency at ang tawag sa kanya is exponential frequency and vibrational frequency. Kasi kalimitan, ang mangyayari niyan, magkakaroon ng solution ang differential equation na typically exponential. Na? Tapos, usually, ang sagot ay exponential to the minus st. So imagine niyo kapag pinag-in natin yung s na yan na may real and imaginary part. No? So ang mangyayari is ganito. Magkakaroon tayo ng function na may e to the minus omega t at e to the minus j omega t. Oh, by the way, yung omega, ang relationship niya dun sa frequency is meron lang 2 pi na value na dinadagdag dun sa or minumultiply dun sa f, no? And this becomes now the radial frequency. Now, what do you remember about this function? Diba kung e to the minus sigma t, and sigma is a real number, like say e to the minus 5t, di ba exponential decay lang yan? And ang itsura ng exponential decay is parang ganyan. Eh ano naman itsura ng e to the imaginary j, no? Omega t, di ba? Di ba ang itong form na to is another way of expressing this form is cosine of minus omega t plus j sine minus omega t. Di ba? Naalala niyo tong expression na to? Na pag may imaginary dyan sa may j na yan, no? It means ganito. Okay? Alright. And ano yan? Cosine and sine yan eh. They vibration yan or sinusoid yan. So, kaya doon galing yung tawag na kung bakit ito ay exponential frequency, itong real part, sigma, because essentially it's the exponential envelope. And j omega is the radial or vibrational frequency because it's the sinusoidal frequency. Okay? And pag kinumbine mo yung dalawa, ano mangyayari? It's like an exponentially decaying sinusoid. All right. Review natin. Nalala niyo yung sabi natin about linear transform, ano? Ang linear system. Ang Laplace transform ay isang linear system. Dahil pag nag-apply ka ng Laplace transform, yung mga functions na yun na nalalaplace transform mo, ang output nila, ganito. Linear transform, Laplace transform obeys homogeneity and superposition. Meaning, kapag may dalawang time signals ka na scaled by A and B, inad mo sila or superimpose mo silang dalawa. Ang output ng Laplace transform nila is just the individual Laplace transforms of the signals times the actual their individual scaling constants A and B. So homogeneity and superposition. Okay. Now, assume natin na all initial conditions are zero. In other words, in parlance, this means the system is relaxed. Walang nakastore sa kanyang energy, no? Its initial velocity is zero, its position is at zero, ganyan, wala siyang acceleration, ganyan, parang ganon. Kung ganon, meron mga properties ng Laplace transform na makakapagpa-dali sa ating pag-calculate sa kanya. If you have a function q of t, you take the Laplace transform. Sabihin natin ang output niya ay capital Q of S. What if you take the derivative of Q of t, kinuha mo yung Laplace transform niya? Ang lalabas sa kanya, ito yung property na yun, differentiation property, S times Q of S. What if kinuha mo yung second derivative ng Q at kinuha mo yung Laplace transform niya? Ang output niya ay magiging S squared Q of S. Do you see the pattern there? So kung ano yung power or order ng differential, ng derivative, yun din yung pang-multiply mo sa kanyang S, no? Kung third derivative ito, S cube lang to, Q of S. Now, kunyari meron tayong I of t or current, no? Kinuha natin yung Laplace transform niya. May mali dito, dapat this is S, dapat ito ay S. Paki-correct dun sa mga mga notes nyo, this should be S, I of S. Kunin natin yung Laplace transform ng integral of I of t. Okay? Ang lalabas sa kanya, the Laplace transform of an integral is 1 over S multiplied by I of S. Paki-change to ha, this is supposed to be S. Okay? S dapat in Laplace space. So, tingnan nyo ha, baliktad ano, pag differentiation, Laplace transform mo multiplied by S, ang Q of S, yung Laplace transform ng Q, no? Pag integration, multiplied lang by 1 over S times I of S. Okay? In the Laplace transform ng function I. Okay? Ang kinainam nitong properties nito, guys, is mapapadali natin yung pag-solve ng differential equation actually. So, tandaan natin, sabi dito, VR equals IR, VC equals integral of I dt 1 over C. PL is equal to DI over DT times L, di ba? Yung kanina. So, ibig sabihin, pag Laplace transform natin to, itong mga voltages na to across these components, capital VR of S is equal just to I of S times R, R being just the property of the resistor. The Laplace transform of the voltage across the capacitor is simply I of S over S, integral di ba? So, ibig sabihin, ito yung gagawin natin, I of S over S, times 1 over C. The voltage across inductor in the Laplace space is equal to, because this is a derivative, then it becomes SIL. Okay. Bakit ito importante, guys? Kasi, ngayon, naalala nyo, di ba sa resistor, ito yung resistance natin. Ito yung nasa ohms, di ba? Ano? B is equal IR. Tapos sabi natin ohmic yung material. Kasi usually yung units ng resistance ay ohms, di ba? And yung mga namin tayong resistor na alam natin basahin kung may mga color code dun sa body niya, no? Ohms. Resistance. Another word for resistance actually is impedance. But the special symbol for impedance is Z. So we can replace R by ZR. Okay? So if in-analogize natin na merong voltage and yung proportionality constant nila ay ang impedance, then we can identify na across the capacitor, itong
itong value na to, 1 over SC, dahil in-isolate natin yung R out, away from it, this would be the impedance of a capacitor. And again, pag in-isolate natin yung R, tinignan natin tong term na to, sabihin natin, ito yung impedance ng inductor. So this is ZR, let's call that CR, let's call this CC. Ano ba yan? Dapat CC to. Again, please correct, dapat CC as in capacitor to. And then ZL ito. And essentially, ang kinainam nito, we can define impedance as a frequency-dependent resistance. Yeah? Frequency dependent. Bakit? Kasi yung S na yan ay frequency units yan. Frequency units yan. Diba? Again, remember, itong S na yan has units of frequency. Okay? Yan. Now that we can express, we can think of this system, no? Para lang silang resistors, no? Kung isipin mo lang sila na resistors na dependent sa frequency. Frequency dependent on frequency of what? What do you mean by frequency of what? You remember, if this is a circuit, we can excite it with any signal. And one of the signals could be a sinusoid, and the sinusoid can be of any frequency. All right? So the reaction of the system would depend on the input frequency. Okay? All right. Okay. Ito yung sabi ko kanina. Observe sabi ko kanina, capacitor, di ba? Ano ang impedance ng capacitor? Di ba? 1 over SC. Okay? At steady state. Ito, di ba? 1 over S. Kung maalala nyo, ewan kung natakal nyo to sa 107, pero parang I suppose na encounter nyo na yung idea ng impedance, ng phasor, ganyan. And perhaps you've seen this expression about the capacitor impedance being dependent on 1 over 2 pi times the frequency times C. I suppose you have seen this before. And where did this come from? This came from, again, go up here, have a look at this, ba? 1 over SC. And remember, S can be sigma plus J omega. O, isalpak natin yung S dyan sa loob na yan. Now, dito natin makikita yung effect ng transient at saka steady state. Itong part na to, tingnan mo ha, pag pinasok natin yan, di ba? Essentially, please remember na pag in-inverse Laplace transform natin, magkakaroon tayo ng parang term na ganito. Okay? Dito lumalabas yung pagkakaroon ng steady state in transient state. Okay? Because this part here, e to the sigma, minus sigma t, siya actually ang nagde-demonstrate ng transient state. Okay? Eventually, di ba, after a long time, mawawala yung effect nito, especially pag negative ito, negative sigma t ito. This term here will at a large t, di ba? Wala na to. Ang maiiwan is this part. Okay? Ang maiiwan is this part. So this part, yun ang steady state. Pag ang input mo ay sinusoidal signal, magkakaroon muna saglit ng konting envelope na ganito, but eventually mawawala yan. What will persist would be the sinusoidal input. Kahawig na ng output. At kahawig na ng output yung sinusoidal input. At ito yung omega dito is nothing but the omega of the input signal as well. Okay? Now, if you see this, no? 1 over SC, and then if you think about the steady state, essentially, ang gagawin lang natin, imaginein natin na zero na itong exponential frequency. When you talk about the steady state, your input is a sinusoid. Essentially, what you're after is the frequency response of the system. Mawawala na to. Maiiwan na lang is parang S equals J omega. Okay? All right? And kung ganon, omega na lang matitira. Eh, di ba omega is just 2 pi f, di ba? So ibig sabihin, yung capacitance, ay yung impedance ng capacitor is proportional to 1 over 2 pi f and then C. And notice, di ba sabi natin, pag mataas ang frequency ng input signal, ano mangyayari? Parang yung impedance is 1 over infinity. Anong ibig sabihin kapag 1 over infinity, di ba zero yon? Ano ibig sabihin ng zero impedance? Ibig sabihin short circuit. Which is why kapag meron kang capacitor sa system mo, no? Tapos high enough yung frequency mo, parang sino-short niya na yung circuit, parang nawawala na yung capacitor kasi parang conducting na yung capacitor kapag high ang frequency. Ayun lang ibig sabihin na, no? Again, impedance is a frequency-dependent resistance. Pero pag DC, DC is zero frequency, right? Kabit mo yung zero dito. Okay? 1 over 0 is infinite, right? Pag 1 over 0 equals infinite, ibig sabihin, open circuit. Walang dadaloy dito. Okay? Now, the importance of knowing the impedance of all these components is because now you can combine all of these in different combinations, just like so, right? And right away, you can express this circuit as a differential equation. But it's messy to deal with differential equations, especially kapag meron pang integral na ganyan, right? So, like for example, this is a loop, a single loop, according to Kirchhoff's law. The V of t is equal to the voltage drops, the sum of the voltage drops. Each of these guys here causes a voltage drop. So according to Kirchhoff's law, rule, V of t, the input signal here, is equal to VR of t plus VC of t plus VL of t, which in terms of the current I of t can be expressed this way, right? Now what if we Laplace transform that? If we Laplace transform that, V of t becomes V of S, I of t becomes I of S, R just becomes R. This integral becomes I of S over times 1 over SC, and this derivative times L becomes 1 of S times L. We can factor out all the i's, and we're left with this. And we can say that this is just the sum total of the impedances. Or in other words, we can think of all these components as resistors. And we can think of that as a series resistors. And all we have to do is just add up their impedances, and voila, we have the total resistance or the total impedance of the system. Right away, we can solve the equation for, say, if we want to know I, for example. Okay. And now, some exercise. So imagine you're given this circuit and you are asked to calculate what's the B out going to be. No? So you have a resistor, and here on the other end, this is parallel capacitor and inductor. And you're going to measure the V out across here. So what is the V out in terms of impedances? So you can express R, no? C and L, yung impedances nila, frequency dependent resistor in terms of functions of S, no? Impedances. So ang tanong is, ano yung V out if you express it in terms of CR, ZC, ZL? Okay? Now, if you think about it, here's the answer. Okay, relax. Here's the tip. Ito lang yan. Isipin mo ganito yan, na? ZR and dalawang isipin mo resistors lang talaga sila. CC and CL. Okay? Now, remember guys, ang nakita kong problema parati ng mga students nag-overthink. They think they need to calculate the current here. They think they need to calculate the current here. Wherein actually, kung iisipin mo, this is just a wire, di ba? And if it's in parallel, no? If two components are parallel, the voltage across them is the same. So if you tap here or you tap here, pareho lang yung V out niya. If you tap here and you tap here, across here, so lang yan. In fact, you can think of it this way, di ba? So CR is here, and then there's a effective resistance here, no? Let's call that C with capacitance parallel to the inductance. No? And think of this as a single resistor. And then, when you look at this, now it looks like a voltage divider. Di ba? And the voltage divider right away, di ba? V out is equal to, if you call this R2 and R1, this is R2 over R1 plus R2 times V in. What's R2? R2 is the impedance of those two components in parallel and over R1, which is ZR, plus again, R2, which is C in parallel. Okay? And remember, di ba pag resistors in parallel, ganito lang yon. If resistors are in parallel, 1 over R effective equals 1 over R plus 1 over R2, di ba? Or essentially, if you solve for R effective, it's just R1 plus R2 over R1 plus R2, right? So C, impedance of the capacitor parallel with the inductor, is just the same, like this. And therefore, V out, V in is equal to, putol. It's just this. CZ over CL over CC plus CL all over CR plus CC, CL over CL CC. Okay? Of course, you can simplify it some more. You do the math and then you simplify and you end up looking like this, right? Okay? So V out is equal to V in times this. Okay? Okay? And here we see that mukha siyang second order system because you look at the form, no? It's almost like a second order system. The denominator is a second order term. Lina ba? Okay. I hope you got it, no? Questions? Good? Okay, I'll stop here. Is there a question? We will need this for our second second experiment. Kindly install vSIM because there's a free academic program for vSIM. Teka, na-upload ko na ba yun? Anyway, upload ko sa it's just 40 megabytes large. It's Java based. So yung installation niya is actually as simple as copying it into your folder. It's a free academic program, but it allows us to visualize what goes on and the frequencies of signals or rather systems just like this. Okay, so please watch out. I'll be posting copy of the pre-academic program for vSIM. I will play with that. So far, may question ba? To summarize, we will have an activity. The first activity is input-output curve because we're going to make a rotation sensor and we need the input-output curve as our calibration curve to convert resistance, which becomes voltage, to angle. Note that when you get that input-output curve, of course, it's at steady state. It's at steady state. With resistors naman, with potentiometers naman, the steady state is once you're finished adjusting it to that angle, then that's it. Steady state na yon, right? But on other sensors that have other behaviors, as described here, you need sometimes to wait. Our next sensor could be the light-dependent resistor. And for that kind of sensor, meron talaga siyang mas obvious yung kanyang transient and steady-state response. We can measure the response of a light-dependent resistor by exciting it with an on-off light source. Okay? And then we can experimentally measure kung ano ang kanyang time constant. And knowing the time constant, alam na natin kung kailan siya mag-steady state. Pero talking about transient versus steady state, actually may interesting ways of observing the transient response. There are, in general, two responses, no? First order response and a second order response. And here, what we've discussed is how do you see a first order response? What's the second order underdamped response? Given the components, how do you figure out kung first order or second order siya? And according to the arrangement, you can have different responses. Depende sa components mo, at saka depende dun sa how you arrange them, you can have a first order or second order response. Okay? Okay. And the reason why we need to know the second order response is this. The behavior sometimes tells us kung nagre-resonate yung system. Resonance. Okay? So yung next experiment naman then would be detecting resonances, but we won't need Arduino for that. Instead, we would need Audacity and just your headphone speakers and maybe a musical instrument. Okay? So yun lang yun.